Hi, my name is Mike Nzundi. I'm a master's student, just recently finished my last semester, um, 2024. Today, I'm going to present to you the project that I did, which called Design, Fabrication, and Testing of Broadband Curved Dipole Antenna for Wireless Communication Systems, with the Department of Electrical and Electronic Engineering. I can give you the basis for this project. In modern communications, that included the 3G, the 4G, and right now we're in 5G. It's more reliant upon the wider bandwidth. So these wideband systems require components such as the amplifiers, the oscillators, and antennas. As you can see here on the picture, that's the picture here, you can see this is a Boeing 787 airplane. You can see it has so many antennas, more than 20 antennas that are protruding, and then for communication, radar communication, and so on. And then on the left side, this is another kind of an antenna, the upper wideband antenna. And then on the lower side here, the first one on top here is the linear dipole antenna. These are the ones that are fabricated for the purpose of this project. And then on the lower side is the curved antenna, the curved dipole antenna, which more look like, if you look at closely, this is how it looks like, but not exactly this one. But on the curved one looks like the one here, right? So in earlier studies, for this to kick off, it's a continuation from the earlier studies that have been done, where people have been studying the multi-feed tightly coupled patch antenna array antennas, which are capable for broadband operation. These were analyzed and designed. So in contrast, this project, we are focusing mainly on the design and the fabrication of a broadband antenna using a single stage dipole antenna versus a linear one, a linear curved geometry of to make additional degrees of freedom. And these additional degrees of freedom will permit the increased flexibility over a control pattern structure and increase the bandwidth operation. That is what we want, bandwidth versus broadband in modern technology. So this design work come into different stages because we have to do the mathematical derivation of the equations. And then from there, you have to do the simulation, and then simulation, the measurement, and then the measurement, you have to get your result. So the first stage of the mathematical derivation is we start with the specification of the far zone, electric field of a general curved dipole. We take look closely the Z, X, and Y plane. We take the electrical field, we multiply it, we wanna get the electrical field. So we multiply the current that passes through that wire, and then multiply it by the cosine of the angle, and then also multiplying by the cosine of the phi angle, which is to do with the propagation constant on the Y plane. After that, then the second stage, we have to do the approximation of the integral equation as a summation. So we chop these wires into very small n sections, because the wire, we can call it a conductor, conducting carrying wire. So after we chop into small sections of n section, then we do the summation so that it will give us the electrical field equation. So then the third one, we come up with the generation of dipole equation. And then from there, we do the Bessel transformation of that dipole equation. Then after that, then the fifth, we have to do the solution of the polynomial equation, where when we do the summation, we take smaller pieces into the Y plane. And then we add them together, and then we come up with the fourth order polynomial. And then if we solve for the YP, we're trying to look at the curvature of the antenna. So when we solve for that YP, we come up with the equation of the dipole antenna, the curvature of the dipole antenna. Then from there, now it's done. Then what we have to do is go to MATLAB. It's a very important tool that we used, MATLAB, and then we try to come up with all this, put it into MATLAB, how we can run it. So MATLAB was the one that generated this pattern, different pattern, which differs also with the frequency. So you can, I don't know if you can see it from a very distant. Underneath here, the one that is bluish, I think it's not so, you cannot see it very well. And then this one, which is more like a brown, it generated those the length and everything for this antenna. So we take these antennas, then to our department, mechanical department is the one that have to fabricate those antennas. And then when they fabricated these antennas, after MATLAB was already promising that what we have been looking for is going to work, because it was promising. There was a symmetric flattening with the curved dipole antenna. Then we fabricated this antenna. Then we do the measurement. Measurements are done in the anechoic chamber with transmitting antenna and then receiving antenna. Then we measure different kind of these antennas in H and E plane. We measure them on the 900 megahertz frequency, then also the 1800 megahertz frequency. And then we measured also including UC Davis facilities, because we're not so sure about our anechoic chamber here, if it's working correctly or not. Or sometimes we have having misleading data, so we've not trusted. So we wanted to compare and contrast with what we're getting at UC Davis with the help of Professor Branner and then some PhD students over there. So we've done that, and then we analyzed after we measured from the H and E plane. Then we were now analyzing the data, what we got. So we were looking for the symmetric flattening of the patterns in all planes, the H and then the E plane, as they're promising, as something that we anticipated before from our simulation in MATLAB. The curved dipole got better results. We are not taking into consideration the fabrication challenges that we faced, because if you look at it, it doesn't look so very nice compared to what we can see on the picture here. Because these wires are very delicate, it's copper wires. And then to come up with a very good curvature of this one, it was a daunting task, because the school doesn't have the equipment for it to be able to measure all that. So it's something that we are suggesting that if the school can be able to put more money into all this, was we have a very good professors that are able to help. And then communication is a very important and essential topic. One worked for Kratos Defense, and then they're looking for people who have background in microwave engineering. And then some of this, I got it from microwave engineering classes that I took at Sac State. So those are the kind of the challenges that we have been facing, and also our anechoic chamber. Sometimes, not every day it will be working. So in a nutshell, that is the basis of this whole project. And then in the end, we're trying also, because it's a continuation, another student who will continue on the aspect of trying to fabricate this on a patch antenna. Maybe the higher the frequency is, the smaller the antenna will be. So when they put it on a patch antenna, then they can be able to come up with an analysis in both types of equipment. This is a wire and then another one on a substrate, a different kind of substrate that they can be using the Rogers substrate, so that they can be able to have a full grasp and understanding of how this curved dipole antenna will behave on a patch antenna. Because in our phone become very small, they have antennas inside. So if we try to put it in a patch, would be more like mimicking what will be on in the phone or any other smaller devices that can use antennas. So that is pretty much. And then I hope with the help from Professor Puma, the one who has been helping me a lot in this project, hopefully maybe future studies will be carried on so that at least the results will come up to a conclusion. That is what I can say in a nutshell of this whole project. And then I would like to thank the whole school for supporting me. Even during this trying times of COVID, the situation is not so good, but I was able to finish it. So that is what I can say for today. Thank you so much. My name is Mike Nzundi again. I'd like to thank you all. Bye.